Hello, welcome to lecture 28 of the course. In this lecture, we will continue our discussion on cavity quantum optomechanics. We will analyze and study the optomechanical Hamiltonian in great details in this lecture. This analysis will help us to understand the physics of optomechanical systems quite well. So, let's begin. In the last class, we have started discussing about cavity quantum optomechanics. Now, cavity optomechanics, as we have learned, deals with interactions between photons and mechanical motion in a cavity. Quantum optomechanics basically deals with the quantum control of mechanical motion to mesoscopic and microscopic system. By mesoscopic, we mean the systems that is intermediate between microscopic, that means atomic or nuclear size system, and macroscopic, which are bulk systems. So mesoscopic system comes in between these two set of systems, microscopic and macroscopic. A typical cavity optomechanical system can be modeled by two mirrors separated by some distance, and out of these two mirrors, one of the mirror is movable, and this whole system is driven by a laser. Typically, it is driven by a laser radiation. And this particular model, where we have two mirrors separated by some distance, out of which one is movable, is capable of explaining many diverse optomechanical system as shown in this figure. And this diverse optomechanical system not only different in their sizes but in masses as well, and mass comprises from gram to femtogram to zeptogram. The underlying physics of this cavity optomechanical interaction is the so-called radiation pressure force, and that also we have discussed in the last class. And radiation pressure force is basically related to the fact that when a photon is hitting an mechanical mirror, it basically imparts a momentum, and the change of momentum gives rise to this radiation pressure force, and that we have discussed in the last class. And we found that the force is equal to 2 times the radiation pressure force is 2 times the power of the radiation divided by the speed of light. Okay, and we also mentioned some important facts about this Fabry-Perot cavity. And in a Fabry-Perot cavity, both the mirrors are fixed and they are separated by distance L. A radiation can enter into the cavity provided it satisfies this cavity resonance condition. Not all frequency can enter into the cavity. This we discussed, and because of this we see that there is a typical intensity spectrum with respect to the frequency, and whenever this resonance condition is satisfied, the cavity is filled up with light or radiation, and all this radiation at this resonance frequency, when it gets filled up, this spectra, as you can see, they have some width, and this width is called the full width half maximum, delta nu FWM, which is also called as the bandwidth. And the distance between two peaks is known as the free spectral range, called FSR, and it is given as C by 2L. And this delta nu FWHM, which is the bandwidth, is related to FSR, or the free spectral range, and the finished by this formula. Okay, and the lifetime of the cavity and the bandwidth delta nu FWHM is related by this cavity uncertainty relation. It shows that smaller is the bandwidth, higher is the lifetime, or higher is the bandwidth, smaller is the lifetime. And also we discuss about the quality factor of a cavity, and quality factor of a Fabry-Perot cavity is given as the ratio between the resonance frequency divided by the bandwidth, or delta nu FWHM. And for a typical Fabry-Perot cavity, you can have it as the resonance frequency divided by kappa, which is the cavity decay rate. This quality factor is related to also finesse by this expression. It is basically an integral multiple. Quality factor is an integral multiple of finesse. Then we went on to discuss the optomechanical Hamiltonian, describing the whole system. The main issue here is that this resonance frequency of this cavity, when this one of the mirror is movable, it's now dependent on position, and this position dependency of the resonance frequency give rise to this expression here. When this displacement of the movable mirror is very small, then you can take it as a quantum mechanical, because this, if you treat it quantum mechanically, this position you can take it as an operator. And if the displacement is small, and if you model it as if the mirror is attached to a spring, then it is going to behave like a harmonic oscillator, and this position operator you can write in this particular form, where x zpf is the 0-point fluctuation, displacement due to the 0-point fluctuation, and it is square root of h bar divided by twice m capital omega m, where m is the mass of the mirror, capital omega m is the resonance frequency of the harmonic oscillator, b and b dagger are the annihilation and the creation operator of the harmonic oscillator respectively. Now utilizing this, we have guessed the Hamiltonian, and this Hamiltonian has several terms. The first term refers to the energy of the cavity mode. The second term here, S bar omega m b dagger b, is the energy of the mechanical mode or the phonon mode. And this third term refers to the interaction between the mechanical mode and the phonon mode. And this final term refers to the laser drive. And as you can see here in this final term, this is explicit time dependency is there, which you can get rid of by going over to a rotating frame of reference. Then if you make the transformation, then this is the Hamiltonian one can obtain, and I have requested you to work it out. I hope you have done it, otherwise we are going to do it in the problem solving session. And only one correction I want to make. Last class I just written this detuning parameter. I wrote it as omega 0 by omega L minus omega L, but it should be omega L minus omega 0. Please keep this thing in mind, and this is important to remember, that detuning parameter is defined as omega L, the laser frequency, minus omega 0 or omega opt, which is omega 0 is the resonance frequency of the cavity, and z is the optomechanical coupling parameter, and which is defined as omega 0 by L into the xzpf, the displacement due to the 0-point fluctuation. And here in the final term, this omega drive is related to the input laser power P in, and it is related to, also it depends on the this cavity decay rate kappa, and also cavity this laser frequency omega L. The optomechanical Hamiltonian so written can also be expressed in a slightly different form. So we can write h is equal to h per omega 0 a dagger a, that is the energy of the cavity cavity mode. And then instead of writing it in the form of b dagger b, let me write it in this form: p square by 2m plus half m omega m square x square. So this is the energy of the mechanical oscillator, and earlier we have written it as h cross omega m b dagger b. So rather than writing it in this form, now I am writing it in terms of p and x. Then we have this third term. This term, let me write here as minus h bar z0 x cap a dagger a. Okay, here z0 is equal to omega 0 by L. Now please note that here also I am not including the laser drive term. At the moment I am more interested in the optical mode, phonon mode, and its interaction only. This way of writing the Hamiltonian can teach us some useful lessons. In fact, we can rewrite this Hamiltonian in this form. H is equal to h per omega 0 a dagger a plus p square by 2m. P is the momentum of the mechanical oscillator. Then I have 1/2 m omega m square. Here I am now writing it as x cap minus h bar z0 m omega m square a dagger a whole square minus h bar z0 a dagger a whole square divided by twice m omega square. You can get this Hamiltonian from this Hamiltonian very easily. I think it's very trivial to get it. Please try to obtain this and verify it that this is correct. So this is the Hamiltonian you are now having. Now you see that this clearly shows certain things. For example, in the absence of light, that means when there is no coupling, we have no, actually not coupling, when a dagger a is equal to 0, in absence of light, no quanta, photon quanta, the mechanical equilibrium happens at occurs at x is equal to 0, right? Because you see this term is going to be 0 and therefore mechanical equilibrium is going to happen at x is equal to 0. On the other hand, in the presence of light, this mechanical equilibrium is shifted to, so you can easily see from this equation that mechanical equilibrium is shifted to x is equal to, from 0 to, it is getting shifted to this point. So you are having it as h per z0 a dagger a divided by m omega m square, and that is greater than 0. This makes sense physically because the radiation pressure force acts to the right. Because the way we have derived this Hamiltonian and guessed this Hamiltonian, you just recall this diagram. If you can see, this clearly shows because of the radiation pressure force is acting to the right. Okay, that's why the shifting of the equilibrium point is also happening to the right. That's why x is greater than 0. Okay, this is the meaning of this thing. Now going back to our usual form of the Hamiltonian, h is equal to h bar omega 0 a dagger a plus h bar omega m, capital omega m, b dagger b minus h bar z, capital Z, a dagger a, b plus b dagger. So this is what we have, our original Hamiltonian without the laser drive term. And for our analysis, we are not considering the laser drive term, and also we are not in the rotating frame of the laser. Okay, that's why there is no detuning term is not there, delta term is not here. We intend to diagonalize this Hamiltonian using a unitary transformation, often referred to as the Polaron transformation. So we are going to use this unitary transformation. So because it's called Polaron transformation, let me write it as UP, P for Polaron, and this transformation is defined as e exponential e to the power z by capital Z divided by capital omega m, a dagger a, b dagger minus b. Okay, Now application of this transformation will result in a new Hamiltonian. H tilde is equal to UP dagger H UP minus IH per UP dagger delta UP delta T, and we have already discussed about this transform Hamiltonian in a previous class in this course. And because this transformation, as you can see, it is not time dependent, therefore this second term here it's not going to be there, so you will be only deal with the first term only. So we have to work out everything term by term. So let me do the calculation, show you some explicit calculation here. So we have H tilde is equal to UP dagger, and let me put H here. We have H per omega 0 A dagger A UP, that one term. Then the second term would be UP dagger H per capital omega M B dagger B UP, and third term would be minus UP dagger H per Z A dagger A B plus B dagger UP. Okay, let us do the calculation term by term. So first let me make this calculation. UP dagger A dagger A UP. Okay, so to do this, let me invoke this Hausdorff-Becker formula, which we have done so many times. Say e to the power lambda A B e to the power minus lambda A is equal to, so we have it as B plus lambda into the commutation between A and B, and then the third term would be lambda square by 2 factorial A commutation between A and B, and you have many terms and so on. Okay, so here let me now write UP dagger is going to be e to the power, we have capital Z by omega M A dagger A UP is equal to B dagger minus B. So because it is UP dagger, so I will have here it as B minus B dagger. Okay, then I have A dagger A, and I have here e to the power, so let me write it actually here to for clarity. Let me write here. So I have e to the power capital Z by omega M A dagger A B dagger minus B. So this is what I have. Okay, now let me take lambda is equal to Z by capital omega M, and here I take B is equal to A dagger A, and A is equal to A dagger A B minus B dagger. Okay, so then term by term if I do that, UP dagger A dagger A UP, this is going to give me first term would be A dagger A. Okay, then lambda is Z by capital omega M, and the commutation between A and B, so we have A dagger A B minus B dagger, and here I have A dagger A. Okay, then we have other terms. So let me first find the commutation relation. A dagger A plus Z by omega M. Let me take out B minus B dagger out. So you can immediately see that you are going to have this term, and this term is going to give you 0. And because this commutation is 0, all the higher order terms are also going to disappear. So you will be simply left out with A dagger A. Okay, now again you have to find out UP dagger, B dagger, B, UP. This actually you can write it in this form: UP dagger, B dagger. You can sandwich here UP dagger between B dagger B. Then you are going to have B UP. Now you can do the calculation in the similarly the way I have done it for A dagger A. You can show that UP dagger B UP is equal to, so it's very trivial, so let me write it explicitly: Z by capital omega M, A dagger A, B minus B dagger, okay, B e to the power Z by capital omega M, A dagger A, B dagger minus B. So this is going to give you, if you do the analysis, you will get B plus Z by omega M, A dagger A. And also very trivially you will get UP dagger, B dagger UP is equal to B dagger plus Z by omega M, A dagger A. Okay, so putting all these things, all these results, we can write the transformed Hamiltonian H tilde in the following form: H per omega 0, A dagger A plus H per omega M, B dagger plus Z by capital omega M, A dagger A into B plus Z by capital omega M, A dagger A, okay, and you have minus H per Z, A dagger A into B plus Z by omega M, A dagger A. I encourage all of you to do it. It's very simple calculation, and you have another term, by the way, that is minus H per Z, A dagger A. This you are going to get it from the third term, B dagger, actually here, yeah, it's B dagger plus Z by capital omega M, A dagger A. Now if you open it up and do the algebra, you are going to get H tilde is equal to H per omega 0, A dagger A, okay, plus H per omega M, B dagger B, minus H per Z square divided by capital omega M, A dagger A whole square. So this is the transformed Hamiltonian we have got because of this polariton transformation. It's called, we have actually used what is called the polariton transform, okay, after applying polariton transform. This is what we got. From this, you can immediately get the energy eigenvalue. It's very trivially, you will see that energy eigenvalue, say Na is the number of quanta in the cavity mode A, and Nb is the number of quanta in mode B. So you can immediately see that you will going to get H per omega 0. Here it would be Na, number of quanta in the, this is the energy of the optical mode, plus H per omega M Nb, this is the energy in the mechanical mode, minus H per Z square by capital omega M Na square. So this is very significant, and it clearly shows one thing. So if there is no coupling between the mechanical mode and the optical mode, that means if this capital Z is equal to 0, you see these are the energy of two harmonic oscillator separately, uncoupled harmonic oscillator in the absence of this coupling. but because of the presence of the coupling, this two harmonic ladder is getting destroyed and enharmonicity is coming into the system, and this enharmonicity which is proportional to a dagger a square, right, and is called Kerr nonlinearity. The enharmonicity uh, which is proportional to a dagger a square, a dagger a whole square, is called Kerr nonlinearity. Kerr nonlinearity. I am sure or assume that you are aware of what is called Kerr nonlinearity. However, let me show you it more clearly by applying the Heisenberg equation motion to the optical mode. If I apply the Heisenberg equation of motion to the optical mode, I have I h per dA dt is equal to a h tilde. Okay, so here I have h tilde is equal to h per omega 0 a dagger a plus h per omega m b dagger b minus h per z square by capital omega m a dagger a whole square. So if I open it up, so this is going to give me I h per dA dt is equal to, I am going to get terms like h per omega 0 a, and then I have minus h per z square by capital omega m, and I have this commutation relation a dagger a square. So let me write it as a dagger a dagger a. Let me work out this commutation relation. So I have a dagger a dagger a. This I can write in this form. So I can write it as a dagger, and I have here a dagger a. Okay, then I have another term. I can write it as a dagger a. I can write as a. I can write it a and a dagger a. Okay, now a dagger is equal to 1, so therefore I have a dagger a, okay, plus a dagger a. Now a dagger is equal to, you see, a dagger, in fact a dagger is equal to 1, right? So because of this I can write it as a dagger is equal to a dagger a plus 1. So utilizing this here, what I can do, I can write this as a dagger a plus 1 into a. Okay, this is what I have, and I have this term here a dagger a. So from here I can write 2 a dagger a plus 1 into a. Okay, this is the commutation relation I have. So what we have then, we have this equation of motion for the optical mode, dA dt is equal to minus I omega 0 a plus I z square by capital omega m. I have here 2 a dagger a plus 1 a, and this I can write also in a different form. I can write it as I omega 0 minus z square by capital omega m twice a dagger a plus 1 a. Okay, now because a dagger a is a constant of motion, we can easily write the solution of this equation, and the solution is a of t is equal to, this point I am utilizing here, a dagger a is a constant of motion. Okay, using this fact I can write the solution as a of t is equal to a of 0, okay, e to the power minus I omega 0 minus z square by capital omega m twice a dagger a plus 1 into t. Okay, this is an important equation I have here. So what it mean? So let us analyze it. It means, okay, by the way, I can write it also in this form. You see the frequency is now getting modified. I have a of 0 e to the power minus I omega tilde into t, where omega tilde, the new frequency is omega 0 minus omega square by capital omega m twice a dagger a, that's the photon number. Okay, this is what you have. Now what it means is that the phase, you can make it out from this equation, that the phase picked up by light inside the cavity, or the light mode, basically phase picked up by light mode is equal to propagation constant k into L. L is the length of the cavity, so k is equal to omega tilde by c, k is equal to omega by c, as you know, into the refractive index in the medium, which is generally equal to 1 we take. So let me not write n0, so let me just write omega tilde by c into L. And you see, in the absence of the coupling, first let me analyze that. In absence of coupling between the mechanical mode and the optical mode, capital Z is equal to 0, and then your phase pickup by light is simply, you are going to have omega 0 by C into L, right? This is obvious. And in presence of coupling, phase, that means when Z, capital Z is non-zero, the phase is equal to 1 by C into omega 0 minus capital Z square by omega m 2 a dagger a plus 1 into L. And what it mean is that now the phase is dependent, or phase is proportional to a dagger a, right? A dagger a, which means photon numbers, and which in turn is proportional to intensity. So overall what you see, because of the presence of this optomechanical coupling, it implies that phi is, the phase is intensity dependent, and you know that is exactly what Carr effect is. So the optomechanical system in the presence of the optomechanical coupling behave like a Carr medium. So far in our discussion of the optomechanical Hamiltonian, we have not discussed the effects of environment or surrounding. We will now see how it can be done. But first, let me write the Heisenberg equation of motion by taking the full optomechanical Hamiltonian into account, including the laser drive time and in the rotating frame of reference. So we have this Hamiltonian, h is equal to minus h per delta, the tuning parameter, a dagger a plus h per capital omega m, b dagger b minus h per z, a dagger a into B plus B dagger, and we have this laser drive term I h bar omega drive A dagger minus A. Okay, here delta is the detuning parameter, it is equal to omega L minus omega 0. Or equivalently, you can write this Hamiltonian in a different form also, as we have discussed. You can write H is equal to minus H per delta A dagger A plus, instead of B dagger B, now I am writing the energy of the mechanical oscillator in terms of the kinetic energy plus potential energy of the harmonic oscillator in this form, P square by 2m plus half m omega m square. Now instead of x, let me write the operator q for the position. So q square, that is the q cap is the position operator. Then I have this interaction term minus h0 h bar z0 q cap b plus b dagger. Okay, this is what I have, and then we have this laser drive term I h bar omega drive, capital omega drive, A dagger minus A. So for now we are going to do our analysis around this Hamiltonian. Okay, the Heisenberg equation of motion can be written down using this Hamiltonian, and the Heisenberg equation of motions are q dot is equal to 1 by I h bar, the commutation between that is going to be qh, and then you have p dot is equal to 1 by I h bar ph, and you have for the optical mode A dot is equal to 1 by I h bar is equal to A h, right, the commutation between A h, and you can easily work out this commutation relation using the Hamiltonian. This Hamiltonian you can utilize, and you can show that you are going to get q dot is equal to p by m, and p dot is equal to minus m omega m square q plus h bar z0 A dagger A, and you will get A dot is equal to I delta A plus I z0 q cap A cap plus omega drive. Okay, so these are the equation of motion that you have obtained from the Heisenberg equation of motion. Now the effects of the environment or the surrounding can be incorporated into this equation of motion phenomenologically. So what we are going to do, we are going to make some assumption. We are going to assume that firstly, let's say the cavity mode decays. Cavity mode is your A cap, right? Cavity mode amplitude decays at the rate kappa by 2, and you have another assumption is that the mechanical oscillator also decay. The mechanical oscillator or the mechanical mode, in fact, mechanical oscillator dampes at a rate gamma m. Also, an input noise, let me write here, an input noise called Langevin noise xi, okay, enters into the system system from surrounding because of the coupling to the surrounding, enters from the surrounding, affecting the mechanical oscillator, affecting the mechanical oscillator. So these are the assumptions we make, and based on these assumptions we can now write the equation of motion in this form. So we have the first equation is q dot is equal to p by m, that remain as it is. The other equation p dot, which is the force, that is equal to minus m omega m square q cap plus h bar z0 a dagger a minus, now I am taking the decay into account, gamma mp plus the noise that is coming from outside, that is the input noise that is coming as an input from the surrounding, that is the Langevin noise, and a dot is equal to I delta minus kappa by 2, because the amplitude decays at the rate kappa by 2, a cap plus I0 iz0 q into a, okay, and we have this omega drive term is there. Apart from this we have to add another term, that is root over kappa a in. This particular term that you see here is has to be added as vacuum noise, vacuum fluctuation noise. So this is a noise term, vacuum fluctuation noise, vacuum fluctuation, actually fluctuation is itself is a noise. So vacuum fluctuation that enters into the optical cavity, this also to be taken into account, because if this is taken into account then only this commutation is preserved, so that you preserve this commutator a dagger is equal to 1 when the cavity interacts with the environment. This equation of motion with input noise terms, which enters into the equation of motion because of the coupling to the environment, are called quantum Langevin equation. So these set of equations are called quantum Langevin equation. Quantum Langevin equation. Okay, and as you can see from this equation that these equations are nonlinear. I will come to that in a minute. One important point I have to make here is that the input noise terms, they do obey certain relations. So first of all, they have zero mean, that means a in average, ensemble average, you can say a in is equal to 0, and Langevin noise, if you take the average you should get it to be 0, and they satisfy correlation functions, say xi of t, xi of at time t dash is equal to twice m gamma m kbt delta t minus t dash. Okay, this is one correlation, and then the other input noise a in t, a in dagger, this vacuum fluctuation noise at different times, this satisfy this condition delta t minus t dash. And then also if you go to the frequency domain, you have a in at omega, a in dagger at omega dash is equal to 2 pi times delta omega plus omega dash. So these correlations are important, and while these correlations are written, it is assumed that the noise at the present time is only affecting the optomechanical system, whatever happened in the past. So it's a kind of a Markovian approximation. However, let me not go into that details, and Only thing is that these noise terms correlations are written assuming that the noise at the given moment is important, and that is taken into consideration here. Okay. Now note that the quantum Langevin equations, as I have said, are nonlinear, and if you look at these quantum Langevin equations, okay, you will see that there are nonlinear terms is entering here because of the fact that there are product terms like qa, as you can see. So you have this term qa, that's a product of two operators, that's a nonlinear term, and because of this the equation become nonlinear, and no exact analytical solutions to the Langevin equations are presently available. However, we can find steady state solutions. So let us write down the steady state solution, and also let me explain what I mean by that. Steady state solution of these Langevin equations. So steady state solution means that this time evolution of q dot and time evolution of p dot and time evolution of a dot, all of them go to 0 in the steady state. Okay. And also we will take denote the steady state solution as this. So a corresponding to the mode a, the steady state solution is alpha bar. For p, the steady state solution would be denoted by p bar, and for q, the steady state solution is going to be denoted by q bar. And if I put this steady state solution here, steady state condition, then in this quantum Langevin equation, for example, this equation itself, you see, if I make the left hand side is equal to 0, then p bar is going to be equal to 0, right? Similarly, you will get the other solutions. So steady state solutions are like this: p bar is equal to 0, and also you can show that q bar, the steady state solution for q, that is going to be, you can easily work it out. You will get it as h bar z0 alpha bar mod square divided by m capital omega m square. And you can also show that the other one, alpha bar, is equal to omega drive. Okay, if I consider omega drive to be a real quantity, then I just put it mod so that it represents real quantity. So, and you have in the denominator, you have kappa by 2 whole square plus delta plus z0 q bar whole square to the power half. So these are the steady state solution of this quantum Langevin equation. And from this equation, I also can write one thing, is that the number of intra cavity photons is given by mod alpha bar square, or simply alpha bar square. Okay, this gives the number of intergravity photons. Now let us investigate the linear response of the optomechanical system around these steady state solutions, steady state values. And this is a semi-classical approximation. So what I'm going to do is, I'm going to discuss the linear response of the optomechanical system, optomechanical system around steady state values, So let's do that, and it's important to do. What I will do here, I am going to assume that every, this dynamical variable here, say you have a, the dynamical variable A, the dynamical variable Q, and the dynamical variable P. They have two parts. One is the classical part, and apart from the classical part, around this steady state value, this steady state value are the classical value, constant classical equilibrium value, and then there is a small time dependent fluctuation, say delta A here. Similarly for Q, the steady state value is Q bar, that is the classical equilibrium value, and around it the quantum fluctuation is delta Q cap, and for P the steady state value is P bar, and around that the fluctuation is delta P bar. Okay, now inserting these answers into the quantum Langevin equation, let me again take this quantum Langevin equation. So let me copy all these equations. So these are my quantum Langevin equation. So if I put these answers in this quantum Langevin equations, then I will get, please try to do that, you are going to get, putting the answers means this is what our answers, okay, this is our assumed solutions that I am taking. Putting these answers in QLE, quantum Langevin equation, you are going to get delta Q dot is equal to delta P by M, and you are going to get similarly delta P dot is equal to minus M omega M square delta Q plus H per Z0. These are very algebraic only, it's very easily you can get it. Alpha bar delta A plus delta A dagger plus delta A dagger delta A, okay, and you have also term gamma M delta P plus this Langevin noise, and finally you are going to have delta A dot is equal to I delta plus Z0 Q bar minus kappa by 2 delta A, okay, plus I Z0 alpha bar plus delta A cap delta Q cap minus root K kappa A in. Okay, now since the fluctuations are very small, we will retain only those terms which are linear in fluctuations, and this approximation is going to remove the bilinear term like this delta A dagger delta A, because that's a small, being delta A being small, delta A dagger delta A is going to be further small. Similarly you have this term, these terms are going to get removed, and if these terms get removed, then you are going to get the linearized quantum Langevin equation. So you are going to get delta Q dot, let me write here, neglecting nonlinear terms delta A dagger delta A and the product term delta A delta Q, you are going to get these equations. Delta Q dot is equal to delta P by M, and you will have delta P dot is equal to minus M omega M square delta Q plus H per Z delta A plus delta A dagger, okay, minus gamma m delta p plus xi. This is equation you will get, and then you will get delta a dot is equal to I delta dash minus kappa by 2 delta a plus Ig delta q minus root kappa a in. Now here what I have done, let me write it a little bit more clearly. This is delta, okay. Here I am defining new parameters. One parameter is z is equal to z0 alpha bar, and this term is called linearized. For obvious reason, this is called linearized optomechanical coupling. Optomechanical coupling. And also I have this term modified detuning parameter delta dash, that is delta plus z0 q bar. It is called effective detuning. It's called effective detuning. Alright, so we have then, these are our linearized, let me write them separately. These are my linearized quantum Langevin equations. These are very important set of equations we get. Now these equations of motion could be written in terms of creation and annihilation operators of the mechanical oscillator as well, and to do that you can again begin with this Hamiltonian, this form of the Hamiltonian. H is equal to minus h bar delta a dagger a plus h bar omega m b dagger b minus h bar z a dagger a b plus b dagger plus I h bar omega drive a dagger minus a, and then you have to take a as alpha bar plus delta a. By now you have understood why I am doing that. And b you can replace by the steady state value, say beta bar plus delta b, that is the fluctuation around the steady state value. Now if you do that and do the analysis in the similar way, you are going to get this set of equations. You are going to get delta b dot is equal to minus, please try to obtain this, I omega m plus gamma m by 2 delta b plus Ig, okay, delta b plus delta b dagger minus root over gamma m b in. B in is the quantum noise that is entering into the mechanical oscillator because of vacuum fluctuation, similar to A in that I have discussed. And then delta A dot is the usual one you are going to get, that would be I delta dash minus kappa by 2 delta A plus Ig delta B plus delta B dagger minus root over kappa A in. These are again the quantum Langevin equation, but this time we are writing everything in terms of the annihilation and creation operator only. So this is called linearized quantum Langevin equations. This is another form. However, it also gives the same physics. Okay, now having this at our disposal, what we can do, we can write down the Hamiltonian corresponding to the linearized regime, and it can be written in this form. So let me now write down the Hamiltonian
or rather let me simply say, using this, let me write down the linearized Hamiltonian. We are now working in the linearized regime. So linearized Hamiltonian can be written as h is equal to minus h per delta dash. This is now the effective detuning parameter, delta a dagger delta a plus h per omega m delta b dagger delta b, okay, minus h per z delta a plus delta a dagger delta b plus delta b dagger. And this we are writing without considering the quantum noise and the damping. Then this is the linearized Hamiltonian, and we are going to discuss this linearized Hamiltonian in the next class.
Let me stop here for today. In this lecture, we have discussed about the optomechanical Hamiltonian in somewhat great details, and we have learned how to linearize the optomechanical Hamiltonian. In the process, we have learned about the quantum Langevin equation in the context of quantum optomechanical system. In the next lecture, we are going to study this linearized optomechanical Hamiltonian further, and we will see how we can extract new physics out of it, and many phenomena arising out of it also we'll discuss in the next lecture. So see you in the next lecture. Thank you so much.